All right, we are starting chapter 10 today, the circle. So quick review of some terminology and vocab words that we have learned last class. Obviously, we've got a circle. You are familiar with that shape. This point in the very middle we call the center. And a chord is a segment where its endpoints are on the circle. And then a diameter is a special type of chord that passes through our circle's center. Now, since we're talking about the diameter, you probably recall from earlier math classes, maybe even as far back to elementary school, the diameter is equal to twice your radius. And since we're talking about diameter and radius, let's review some other formulas hopefully you already know. The circumference of a circle, the distance around the outside, is 2 pi times your radius, or just the diameter times pi. And the area of your circle is pi r squared. So I'm just going to put those up there in case you need those later on for review. But we are focusing today on chords. When we measure the distance from the center to a chord, we do it with a perpendicular segment. So from the center, you would draw a perpendicular segment, and what it does to that chord as well is it bisects it. And then remember, the radius is the same from any point on the circle to the center, but when we're working with these problems, we want to be strategic, and if we draw it to the end point of the chord, we have a right triangle, which means we can use Pythagorean theorem or other right triangle knowledge that we have from previous parts of our school year. So let's start with practice problem 1. The radius of circle O is 13 millimeters, so I'm going to start with a circle. And if it's called circle O, that means that my center point is O. So like if we had circle A, that center point would be called A, etc. Then we've got the length of chord PQ is 10. So anywhere in the circle you can draw a chord, and its endpoints are P and Q. And we want to find the distance from the chord to the center. So again, that's going to be that perpendicular distance. And what this does is splits PQ in half. We were told PQ was 10, so each of these is going to be 5. And my radius is 13, so I'm going to strategically draw that in from O to Q to form the hypotenuse of this right triangle. And so then to find that distance, you could either use Pythagorean theorem or recognize that this is one of our triples. This is going to be a 5, 12, 13 triangle. So it is 12 millimeters away from the center. On number 2, find the length of a chord that is 15 centimeters away from the center of a circle with radius of 17. So I'm going to draw another circle with a chord in it. And I'm looking for the chord's length. I know it's 15 centimeters away from the center. So again, that's this perpendicular distance. So this is 15. And I know that the circle has a radius of 17. I'm going to draw that in to form a right triangle. And again, you can use Pythagorean theorem, or this is an 8, 15, 17 triangle. But this 8 is only half of the chord, so the whole thing is going to be double that, or 16 centimeters. Now these next 3 theorems just reiterate what we have already explored. If the radius is perpendicular to a chord, then it bisects it. If a radius of a circle bisects a chord, it's not the diameter, but it is perpendicular to that chord. And the perpendicular bisector of the chord passes through the center. So all of those theorems are used to solve these types of problems. And so on 1, we were finding the distance. On 2, we were finding the length of the chord. On 3, we are going to be finding the radius of a circle that has a 24 centimeter chord 9 centimeters away from the center. So I'm going to draw a chord down here, and I know it's 9 centimeters away from the center. The whole thing is 24, but it is being split into 12 and 12. So to find my radius, I'm going to draw that in here to form a right triangle. And again, I've got a Pythagorean triple. This is a 9, 12, 15. So 15 centimeters is the radius of this circle. Okay, last one, and this one's going to be a little more involved. I've got 2 circles that intersect and have a common chord 24 centimeters long. So I'm going to start by making my 2 circles that are overlapping, and these 2 intersection points are going to be where the common chord goes. And we know it is 24 centimeters long. The centers of the circles are 21 centimeters apart. So there are my 2 centers, and they are going to be 21 apart. And I know the radius of one circle is 13. So I'm going to draw in that radius first here. Here is my 13 radius. And if I draw in the distance to the chord, again, it's going to be perpendicular and it's going to split that chord in half. So the 24 gets split into 12 and 12. So this means I can use my Pythagorean triple to find that this distance here is 5. And I'm going to go ahead and highlight it yellow, which might not come up super yellow. Oh, it did. Okay. So that distance is 5. Well, I know that the total distance between the two centers is 21. So if this increment is 5, the remaining distance to the other center, or my blue, has to be 16 because 21 minus 5 is 16. So if this is 16 and I draw in my other radius, well, this is a 12, 16, 20 circle. So the radius of the other circle is going to be 20 centimeters. Okay. Still talking about chords, and in this case, congruent chords. Two chords are, if they are equidistant from the center of the circle, then they are congruent. So if I've got a circle and chords AB and CD are the same distance away. So again, we're talking about that perpendicular distance here. So if I know XP and PY are congruent, that means the chords themselves are also congruent. And this is true vice versa. If I know that the chords are congruent, I know that they're going to be the same distance away. So looking at example 1 here, in a circle, I've got chord AB, that's 3.25 centimeters long, and chord CD is 3 1/4 centimeters long. Which chord is closer to the center of the circle? Well, 3.25 and 3 1/4 are just different ways to represent the same increment. So this means that AB is congruent to CD. Therefore, they're going to be the same distance away, or equidistant. And this comes from Theorem 78. Okay, let's throw some algebra in there. If I've got circle O and I know that chords A, B, and C, D are congruent, then OP is 12x minus 5 and OQ is 4x plus 19. We want to find the length of OP. Well, just like I talked about in problem 1 here, if the chords are congruent, that means they are equidistant from the center. So OP and OQ are also congruent. So that means I could say that 12x minus 5 is equal to 4x plus 19, and I can just solve this equation for x using algebra. So I now know that x is 3, so to find OP, I'm going to plug it in here. So 12 times 3 minus 5, that's going to be 36 minus 5, which is 31. Okay, last question. We got a fly sitting at the midpoint of a wooden chord of a circular wheel. So I've got a circle with a chord on it, and the fly is in the middle. That is where my fly is. The wheel has a radius of 10 centimeters, and the chord has a length of 12. I want to know how far he is from the center. So again, that perpendicular distance, I'm going to draw my radius in here to make a right triangle, and I know that the radius is 10. If my chord was 12 long to begin with, it's now been split into 6 and 6. So this is going to be a 6, 8, 10 triangle. So the fly is 8 centimeters away from the center. And that wraps up our first day of notes from chapter 10, covering sections 1 and 2.